Okay, so it's recording now, and I invite everybody to uh, turn off the microphones, except Rodrigo, of course, to avoid. Okay, more people are joining. Okay, okay, so welcome everybody. Good morning, and it is a great pleasure to have Professor Rodrigo Negreiros today as our speaker. So Rodrigo is also my colleague at Universidade Federal Fluminense. So it's a great pleasure to have him here. Also, to give a different perspective on the topic, because typically here we have the, let's say, the gravity side of the story, and Rodrigo is here today to bridge some gaps and to provide some links with I'm sorry, because I am letting people in and introducing Rodrigo, and it's too much for me. Uh, but so Rodrigo is here today to bridge some gaps and talk about how neutron stars can be a very rich arena to understand physics under extreme conditions. And for those of you that don't know Rodrigo, he obtained his bachelor degree as his master degree at Universidade Federal Fluminense, and his PhD by San Diego State University and Claremont Graduate University. After that, he moved to Frankfurt, and he did a postdoc there. He was a postdoc at Frankfurt Institute for Advanced Studies. And since 2012, he's a professor at the Physics Institute at Universidade Federal Fluminense. Rodrigo is extremely productive. He has several different contributions to the area of compact objects, neutron stars, and nuclear physics. Also, he is very active in our graduate program at Universidade Federal Fluminense, as not only giving lectures, mentoring students, but also in the hardcore bureaucratic stuff. And also, he obtained relevant grants in Brazil as the Jovem Cientista do Nosso Estado, from FAPERJ. He's a researcher, well, I would say a CNPq researcher, but I don't know if this is the best way to say that. But and it is my pleasure to give the stage to Rodrigo now to present his talk. So thank you very much, Rodrigo, for being here, for giving the talk, and I will shut up now for you. So.
Well, thank you, Antonio, for very warm introduction. It is actually my pleasure to be here and to talk to you. And I hope it will be an enjoyable experience for everyone. And as Antonio said, I do apologize. A few of my slides, they have, they're in Portuguese, but most of them are in English. But so if for those of you that don't read Portuguese, here it says probing nuclear a high energy nuclear physics with compact stars or neutron stars. And as Antonio said very appropriately, I'll try and bridge the gap between the gravity theory and basically general relativity and high energy nuclear physics, which is mostly what I do. So I live kind of in both worlds. I have one foot in GR and another foot in nuclear physics, and I try to play around with those two things. They're very cool things. Don't have to tell you that. And they usually, what happens is neutron stars are very extreme, as you probably know, and they're very nice sandbox playground for us to test or to try to test some things in very extreme conditions. And I try, as well as a lot of other people, try to do that. So before I begin, I have to apologize a little bit, especially to you, because I usually give talks like this to a nuclear physics audience, which don't have much of a background in general relativity. So the beginning will be very obvious to most of you, I believe. So please apologize, and I'll try to skim that to go through that very quickly. But I'm not trying to, to be a little bit condescending here. It's just that usually I have to make an introduction about GR to a different background. So I'll try to paint a general picture, and afterwards move to more specific things that I'm looking into and that I'm doing. So as a very initial introduction, let's talk about high energy astrophysics. That's what it says over here, right? And it's important to know how we can look into those things. And as you probably know, that there's been a revolution, and we are living this revolution in astronomy and astrophysics in this past 20, maybe 30 years. When I began studying this, we were on the cusp of this, shift, right? But back in like 2005, 2006, we had very scarce data on neutron stars. There were some data, but not nearly as close as we have today. And basically, our horizons have been broadened, especially due to the advancement in technologies. And most of the things that I like to do, I like to keep it grounded to some observations. So some of the things that have happened in the past 30 years have to do with a few satellites emissions. Some of them are still going on, and some of them have already ended their life cycle, and some new ones that they're coming online. So XMM Newton, for instance, it's a satellite that we use to detect gamma rays and X-rays. We have the Rosat satellites, also used for gamma ray detections. And I don't really recall all of the details, and if you ask me which one of them I'm online today, I wouldn't be able to tell for sure, but I think Rosat and XMM Newton are still online, but I'm not sure. Oops, sorry, something happened here. What's going on? Okay, so we have the very large array. This is a very important instrument for us especially for radio astronomy. We have the FAST, and this is a brand new radio telescope that I have had the opportunity actually to visit. It is just incredible how quickly it was built and how powerful it is. And so this is the beginning of the construction, and this is through the construction, and now it's online. I was over there in 2019. It was already functional, but it was not open for outside time. Basically, you had to be connected with someone in the project to use it, but now they are accepting applications for usage for everybody. It's very powerful, very high, very sensitive satellite. Not very precise, but very sensitive. It's actually very good for radio astronomy. And of course, we have this square kilometer array. It's also for radio astronomy that should be coming online maybe in the next few years in South Africa, I think. Also, it's promising, very promising for radio astronomy. And why this is important for the stuff that I do. I'm not an observer. I don't do observations. I work with people that do observations, and I use their data, but I don't actually, do the instrumentation of those things. Of course, we have LIGO, and I have to tell you about LIGO, and you probably know this better than I do. So here's a very nice graph. You might have seen it before that shows us, not taking into account, of course, gravitational waves, what can we see and what we can't see from the surface, from the space. So basically, as you know, our atmosphere, luckily for us and for life on Earth, it's very opaque to it's not very transparent, let's put it this way, to gamma rays, X-rays, and ultraviolet. So you can see the opacity over here. Basically, high energy photons are completely blocked by our atmosphere. So we have no hope of seeing high energy photons from the surface, which is bad for astronomy, but it's very good for life. Right, so then we need satellites in order to do that, and that's why we have those satellites that allow us to detect these high energy photons. We have visible lights. We have very narrow window in which visible lights, mostly transparent to visible light, in which we can do traditional optical astronomy. Then we have some area of interference over here, microwaves and all of that. And then infrared is also mostly absorbed. And then we also need satellites for that. But this, for me particularly, is not very interesting because we don't see very high, long wavelength emissions from neutron stars and high energy astrophysics. But if you want to do solar astrophysics or even planetary astrophysics, and then you need satellites in order to detect this infrared spectrum most precisely. Then we have a large gap of radio that's mostly transparent, in between maybe 5 centimeters to 10 meters of wavelength, and that's where most of the radio telescopes shine, right? And that's where we can get a lot of information from radio astronomy. That's also interesting for us in compact stars physics. But then we have long wavelengths that of course are blocked. But then again, for compact stars, is not very interesting. It's interesting for large scale other things, but not for compact stars. So what has this new technology that have allowed us to detect high energy photons allow us to do? It basically allows us to have a new set of eyes to look to the universe, right? And then we can detect radiation, high energy radiation coming from accreting neutron stars. Okay, so basically, of course, this is not a picture, it's just an artist's interpretation that I find very pretty. And then we can see not only the jets coming from here, but also we have this compact stars that are intermittently accreting matter, and then they eventually emit flashes of X-rays from the surface. This allows us to do a lot of physics in the outer layers of the neutron stars, basically thermodynamics and things like that. But we can also detect high energy photons coming from the jets and things that we can learn from that. Of course, gamma ray bursts, which is not something that I do very often, but there's a very, very, very large community studying gamma ray bursts, and we have short gamma ray bursts, long gamma ray bursts, and I could go on for a very long time just talking about gamma ray bursts. They're still mysterious in some ways. Okay, the long gamma ray bursts, most people accept they come from a collapse of very massive stars and the birth of black holes. But then still some modeling to do, and then you can have coalescing neutron stars giving rise to gamma ray bursts. There's a lot of numerical modeling going on through that. And then, of course, one of the things that I'm very, very much interested in, and not most of the things, but a lot of the things that I do are associated with this. And that's the cooling, or the thermal cooling of neutron stars. And here's a picture, of course, a multi-wavelength picture composed by several wavelengths of the Cassiopeia remnants. So this was a supernova that was observed by the Chinese, I think, about 400 years ago, more or less. And today we can see its remnants. So basically, this is all the matter that has been expelled from the supernova, and it's about the ideal time that we can observe a hot neutron star, or relatively hot neutron star inside, because it's a remnant, and all of the matter that has been ejected, it's already transparent to X-rays. And this is good because we can see right here, I don't know if you can see over there, a very bright X-ray, well, not very bright, but a relatively bright X-ray spot. It has an emission mostly as a black body emission. And it is, all evidence points out that that's actually a neutron star that's cooling down. It's very unlikely that it's not. And I probably will talk more about this towards the end. And this is one of objects that we were very lucky to observe that it's actually so hot, I mean, again, relatively hot, that people have continuously observed it for 20 years, from 2000 and, well, maybe 15 years, 2000 to 2013, and they could actually measure how its temperature changed, or its luminosity changed during this time. It's very little, so you need very sensitive instruments for that, because of course the time scale for the cooling of a neutron star is millions of years. So in order to see how the surface changes, the surface luminosity changes in such a small time window, it requires very precise instruments. So there's still some uncertainty on how much it's changed, but we can clearly see a slope there, which is actually very interesting. And of course, supernova, that have several, applications and several things you can study, from cosmology using as standard candles. If you have supernova type 1a from white dwarfs, I am mostly interested in supernova that are core collapse supernova. That's the birth of usually compact stars. But several things you can do with supernova, you can observe in, of course, several spectrum. And of course, now it's, all the talk in the world and everything is talking about the merger of black holes, right? Because then you can have, we have observed gravitational waves from this, and several things we can learn from. Again, I am mostly interested in the merger of neutron stars, which have also been observed in the gravitational wave spectrum, but also neutron star, black holes, and things like that. But of course, it's a very nice playground, especially for gravitational physics and for high energy physics. And there's a lot of simulations going on over here, and things are very interesting. So, and then there is the other end of the things that I do, that I also talk to these guys, so I'm right in between, which is high energy nuclear physics. So things that happen in particle colliders, such as the RHIC, relativistic heavy ion collider in Brookhaven, and of course the LHC, particularly to CMS and Atlas and things like that, that we also need to have some information coming from these guys, especially regarding the interaction of fundamental particles and hadrons and all of the things that I'll try and clarify and make it clear why do we need those two things and how we can bridge this gap between those two things. So those are some of the people that I'm also in touch with, mostly through a few results. And this is the reason, right? This is a diagram you probably have seen. I don't even know who's made it. I did ask permission to use. I think, that was Fair who made it. Fair was a collaboration that was in Frankfurt at the time, and they somebody over there made it, and they allow us to use it. So basically, this is a very pictorial phase diagram of barium matter, right? Okay. So what we have here is temperature, and we have here is net barium density. Usually we make this diagram with the chemical potential because that's more accurate. But we can also make with net barium density. That's easier to understand. Of course, what we actually know about this diagram is almost nothing. We know pretty much what happens over here in this arbitrarily defined one net barium density, which is where we live, right? We have very low temperatures. And of course, when I mean low temperatures, I mean in relation to the chemical potential and to the nuclear and the strong interaction energy, right? And that's all that matters to me. So have very low temperature and very low net baryon density. And then you have the quarks basically form protons and neutrons, and that's the natural states, and protons and neutrons make nuclei. And then we have atoms, and we have all the chemistry and everything that we know. So what Rick and LHC and these particle colliders do, so if we were to cover what we actually know, we have a huge black, everything would be black with the exception of this and maybe here, right? And what Rick and experiments in Rick and LHC do, at least those that I'm interested in, they do several other experiments, but those that I'm interested in with a very high energy output, is basically probe this region over here. It's a very high temperature, right? So we have very high temperature. And some people, especially students, might be confused. Well, is it low density if you take, like, I don't know, some gold nuclei and accelerate it to 99.9% of speed of light and then collide those two things? Why is the density low? Well, it's a low chemical potential, actually. It's a net density that's low because, you know, we have a lot of particles and antiparticles, and then the chemical potential basically goes to zero. And this is like conditions we expect it to be, you know, similar to those in the early universe. So they don't really apply in terms of neutron stars, because neutron stars, they actually live on the other end, okay? Well, but of course, the underlying physics should be the same. So if we learn something about the interaction here, we can apply it over here and vice versa, right? What we can't do is actually take whatever, expect to find the phenomenological behavior of matter in this end to be the same as in this end, because it's not. Physical conditions are different, but then the nature of the interaction should be similar. And neutron stars, as I said, live on the other end, right? And they have very low temperatures. And then it's going to sound crazy because you say, well, we're saying the neutron stars have low temperatures because you're studying the cooling of neutron stars. Yes, they don't have zero temperatures, and I'm going to try to clarify how we can do the cooling. And luckily, the cooling of neutron star is dominated by weak interactions. So basically, in terms of the strong interaction, the neutron star has a zero temperature because its temperature in the cooling is about, it starts at 1 MeV and then it cools down from that. So basically, all of the thermodynamic processes that take place in the neutron star after it's born, it's basically weak interactions in the keV range, right? So basically, beta decays and things like that. So the cooling is dominated by weak interaction, whereas the equation of state is dominated by strong interaction. This is very fortuitous because then we can decouple those two things, right? We don't have to worry about the temperature when we model the equation of state. We can just basically model the equation of state with a zero temperature equation of state, because for the strong interaction, which is the dominant interaction that generates pressure, the temperature is pretty much zero, right? It's about 1 MeV at most, so we are really, really down here. So neutron stars should live over here. And now we expect to have a phase transition to it's very pretty much accepted that we do have this quark-gluon plasmas. If we go to very high energy, then we have asymptotic freedom, and we should have quarks behaving pretty much as if they were free. What we don't know if that happens and this is a big problem nowadays for people that are studying equation of states, is, well, do we have a phase transition happening between the star? Do the chiral phase transition and the confinement phase transition happen at the same exactly place? Basically, you can have this banana region here, you can have the confinement and then chiral transition, or they could be just aligned and they could happen at the same place. Do we have color superconductivity? If we do have phase transition, if we have neutron stars with quark matter in its interior, do they have pairing? A lot of things that we're trying to answer. And this is actually a big problem now, because Most of the observations that we do have, especially most recently, point out to very massive neutron stars. We have low massive neutron stars, 2, 1.4, 1.6, several of those, but we're also having more and more neutron stars of very high masses, with 2.0, 2.1, 2.2, and small radii. Right? Even though we can actually measure the radii, we're getting better on that, but not as precisely. We have a very good upper limit, and we know that its density, the average density of neutron stars is very high. Okay, yes, so we have a question here about, let me open the chat. Yes, so we have to be very careful with the names that we use because there's a lot of confusion. Quark stars, it's a different thing. Okay, so quark stars are a hypothesis that I'm not going to cover here, not very much, although I do work with that. The Witten hypothesis that quark matter is the absolutely ground state of matter, of baryonic matter, right? So basically, everything is a matter state, and then if you go to high enough densities, you could convert everything into. Sorry, let me just put this. My thing is beeping over here. Let me turn this off so I don't have to do this. Okay. So this is quark stars. Okay. This is a hypothesis that we can rule in or rule out because we don't know exactly that depends mostly on the surface tension of quark matter. It depends on the mass of the strange quark. It depends on a few QCD properties that we don't know exactly. So if that were to happen, there would be some observational signatures of that. But it's hard to, so that basically could be what they call a quark nova. It's a conversion of this and the release of energy. But they could be confused with regular novas, so regular supernovas and things like that. So there's no smoking gun so far for those things. But what I'm talking about here is not quark matter in the sense of absolutely stable quark matter. We're talking about a phase transition to a quark matter state that's not absolutely stable, but if you go to densities that they're high enough, then you start to overlap so you basically cover. You go through this phase transition to this quark-gluon plasma, but at low temperatures. So this is not very esoteric. This is expected to happen in the traditional standard model. We just don't know at which density that's supposed to happen. And we don't know if the first order phase transition is the second order phase transition or things like that. And this transfer does not release a lot of energy. Even if you have a neutron star that becomes denser, usually you have some latent heat from the phase transition that would basically heat up the star. The problem is, if you go to this quark-gluon plasma, everything we know now from QCD, it's actually a crossover. Yeah, well, some people say it's a crossover. It could be. Okay, so I thought, yeah, I'm sorry. You're saying a low density. Yes, over here it is a crossover. You're completely right. So Wolfgang says that I thought a low baryon density is actually a crossover, not a phase transition. Its temperature is also known from Lattice QCD around 155. Yes, absolutely right. I don't remember exactly the exact number of temperature, but 155 sounds about right to me. And it's completely right. There's not a phase transition over here. It's a crossover from this state to this state, which is kind of why it's tough to say which temperature that happens exactly. But about 155 sounds about right. But what I'm talking about is low temperature. We don't know if it's at low temperature, it's also a crossover. It's a first order phase transition or a second order phase transition. That's the things that we don't know at low temperatures and high densities. There is an experiment that's supposed to come online in FAIR. That's a CBM, compressed baryonic matter. That's hopefully will, illuminate this a little bit. So basically, it's tough because we need to do, it's not high energy. You have to go to lower energy. So we don't have to collide those things with a very high energy, but we have to do it at lower energies. Of course, we can never get to neutron star temperatures. But hopefully the fair will, it's happening in Darmstadt, we'll be able to go through maybe this region here and tell us if this is a crossover or first order or second order, and hopefully this will help us understand this. But in terms of neutron star, one of the biggest problems that we have now is the following. Everything we know, if we have quark matter in this regime over here, basically the quarks, they become massless or almost massless. So we have a very soft equation of state. And this is an issue. You have a phase transition, you soften your equation of state. So basically it doesn't generate as much pressure. And you have a very difficult time trying to explain high mass neutron stars. So nuclear physics is telling us that at the densities that we are observing, neutron stars should most likely have a quark matter core in its interior. But when we try to model this, we don't reach the high masses that we have. And then we have to do all sorts of things, and put a repulsive vector interaction in the QCD model that we use. Of course, all of those models are phenomenological because we can't solve QCD and all the things to try and solve this. But this is an open problem that people are really looking into. So if we go on, okay, so I'm going to skip this very quickly because this I usually give a very overview of general relativity to my nuclear physics colleagues. Not that they don't know, but usually they have students and things like that. But I think I can skip this very easily for you guys. So basically talk about special relativity and general relativity, a change of paradigm, and how, and I explain very quickly the thought experiment from Einstein, from the rockets and the elevators, and how we can impose the equivalence principle and how that works. But I think I can safely skip this. So one of the most famous solutions, again, I'm going to go very quickly through this because I think this is very obvious to you. Schwarzschild solution. And I usually talk, this is interesting for us because of some observations that we do too about the effective potential of a spherical solution and how we have a very different effective potential when compared to Newtonian potential that we have a maximum here. This for different values of angular momentum. I mean, if you guys are interested, I can talk into details, but I don't think I have to. And then I talk about a few orbits, the shape of the orbits, and the problem of the Mercury perihelion and how it's solved, the precession of the Mercury orbit and how we can solve this. And coming back to more observational stuff, one of the most recent before gravitational waves direct observations, one of the most strongest evidence of gravitational wave was the Hulse-Taylor pulsar, right? And then we have the Hulse-Taylor pulsar, the two pulsars, they are orbiting each other. And Hulse-Taylor predicted how their orbit should change in the cumulative shift of its periastron time. And it's a fantastic agreement with what you expect from the emission of gravitational waves. So every time they go through this orbit, they emit gravitational waves. So at the time, I think that was 1997. I could be mistaken. Of course, there were no technologies to detect the gravitational waves directly, but this is a very strong evidence, and deservedly, they got the Nobel Prize for this. So why does this matter? Why do we do this? What can we expect to learn other than it's cool and it's fun and we like it to play around with this and look at the universe? Is there something that we can learn from this? Of course there is. Oh, I'm sorry, let me skip this. This is also gravitational wave, but coming back from this was a leftover from a previous talk. So the idea is to understand this part of the phase diagram and to use observations, and more we have more data that we can use to fine-tune and to basically, not fine-tune sounds bad, but to refine our models for the strong interaction and combine forces with experiments and hopefully understand a little bit more about the Lagrangian of the strong interaction, the phase transition, and what happens at very high densities. And hopefully this will help us understand not only the universe as, astrophysics phenomena, but also high energy physics. So going back to compact stars, as I said, compact stars in particular, those that I'm interested in are neutron stars. A little bit of white dwarfs too, but I'm not going to talk about white dwarfs today. They have a different evolutionary track than the compact stars. And today I'm going to talk about these objects that are born after core collapse supernova. I think everybody knows what's a core collapse supernova, but just in case, I'll briefly say what's the difference between a core collapse supernova and, for instance, type 1a supernova, right? A core collapse supernova is basically a massive star that has gone through all of its fusion cycles until it reached a relatively small iron core on its core, right? So basically it's, burned through hydrogen, helium, carbon, nitrogen, until you got into the core. Of course, this is not the whole star because it burns in layers, right? You have a higher fusion rate at the core because it's denser, it's hotter, so it's much easier to go through the Coulomb barrier in the fusion. So we have a higher rate of fusion in the core. So it's like an onion, right? If you take a star at some point in its life, it's going to have a lot of hydrogen on the outer layers, but if you go inside, it's going to have higher helium and so forth. Not all the stars are able to burn all the way through to iron because sometimes when they get to carbon, for instance, our sun, the sun, when it gets to carbon, is going to expand because it's a more energetic fusion process. And then it's going to have a high radiation pressure, and gravity is not going to be able to hold it, so probably it's going to just evaporate. It could. This is some, I don't know exactly the models, but I think some people have studied this about how a white dwarf, if it's accreting enough, could become a supernova, a neutron star, but I'm not absolutely sure. Most of the times they do explode in a 1A, which is the difference, for instance, that a core collapse. So in the case of the sun, for instance, once it expands, it just basically ejects in a non-explosive manner its outer layers because of the radiation pressure. And what's left behind is this very compact, not as compact as a neutron star, but it leaves behind a white dwarf, which is basically an object it doesn't collapse due to the degeneracy pressure of electrons. Okay. A core collapse is not like that because you go through iron, and then instead of so basically the white dwarf is born due to the fact that the radiation pressure wins over the gravitational pull, right? And then the radiation pressure ejects everything and leaves a core over there. A neutron star is the opposite. Once the star, a massive star, reaches an iron core at its center, then its radiation pressure at the center ceases to exist because you can fuse iron in an exothermic process. So basically, you drop drastically its radiation pressure at the center, and then the gravitational pull wins over radiation pressure. The equilibrium ceases to exist, and the whole thing implodes. Then a lot of things happen, and I'm going to go into details over here. Also, because I don't know much, the simulations are not a lot of people don't know, but there's a lot of problems when we simulate those things. We cannot make, most of the time, we can make the simulation explode. Usually the explosion dies off and need a trigger and things like that, but it's not my specialty. But basically, it explodes and leaves behind the iron core becomes a neutron star. That's the core collapse supernova. A type 1a supernova, for instance, as was mentioned in the chat, is the collapse of, it's not a collapse, it's the explosion of a white dwarf. So you have white dwarf, there's a bunch of nuclei in a lattice, in a crystal lattice, with a bunch of electrons acting as a electron degenerate gas. But if it's accreting matter, then you make the nuclei into the lattice, which is cold, but then you compress them and they go through fusion processes. And then you have a thermonuclear explosion, a chain explosion that happens in the nuclei. So all of these nuclei start to go through a fusion, and they basically explode. And this is very nicely modeled in the simulations. So, but it has nothing to do with gravity, or not as much as this. So what's left behind is a neutron star. As you know, our estimates based on observations indicate they probably have around 10 to the 27 baryons, mass between 1 and 2 solar masses, actually 2.2, 2.3 with the recent observations. Radius, and I'm being conservative here, but the radius could be up to 10 to 15 kilometers. But most observations recently, and now we're getting better and better in this, indicate they have small radius, maybe 12, but it's not settled. And then we have, yes.
Just taking the opportunity, because there was a question in the chat by Luis regarding the radius.
Oh, nicer. Yes, I didn't see Luis. It is precise. Well, I don't know. It's very political question. I don't want to get into this. I like NICER, just to be fair. I think NICER is doing a great job, and I think the results are being very helpful. I do think, and this is personal, and it's shared among some other colleagues, they're being overly, let's say, optimistic with the error bars. I don't think their results are as model independent as it seems to be. There are a few things over there, but they are the best that we have so far, and that's for sure. And that's what I'm basing this estimate of 10 to the 12 kilometers about the NICER estimates about this. And of course, we don't have a large set of results so far, so we cannot say that that's for all of the stars. But yes, I think they're very precise when compared to what we had. But I don't think they're as precise as they seem to be. And let's leave it at that. So there are strong magnetic fields, there are strong electric fields, and relatively high temperatures for our standards, but low temperatures for nuclear standards. There are several observations of neutron stars in several natures, and usually I like to use the example of the elephant, but I don't think I'm going to do that here. So most people confuse pulsars with neutron stars as they are synonyms. They are not. Most pulsars are, in fact, neutron stars, but not all of the pulsars are neutron stars. We have at least one or two white dwarfs that also pulsate as a pulsar. So basically, the pulsar is one of the different manifestations of neutron stars that we can see, because it's relatively easy to measure. We just need a radio telescope. And if you have a rotating neutron star, and we have magnetic field, and then we have radio emission. And if we're lucky enough to be in the part of the light cone that goes through us, then we can measure this pulsating. Okay, this is the very general picture of what we think we know about neutron stars. So the outer layer is pretty much settled, and I think we have a pretty good idea of what's happening in the outer layer. And by the outer layer, I mean the subnuclear densities, all of the regions that are below nuclear matter saturation density, okay? Because those are regions that we can relatively well simulate here on Earth. It's not exactly the same because the temperatures are different, but we have a good idea with a few caveats that I'm not going to go through here. But basically what we have is a structure in this region here between 0.3, 0.5, maybe 1, rho zero is the saturation density. in which we have a lattice. It's similar to a white dwarf structure, so we have a lattice of ions sitting on this lattice, and a sea of electrons that's basically providing pressure. So it's a crystalline and a hard structure that have very important consequences for the thermal evolution, because it's basically a crystal. Then we have atmosphere. Then as we go through supernuclear densities, then maybe between 1 and 1.5 saturation density, we also have a relatively good idea. We know we have neutrons, protons, and electrons. As we go through higher densities, maybe above 2 saturation densities, that's a big question mark. What do we have there? Do we have a quark gluon plasma? Do we have hyperons? We know hyperons exist. So basically, hyperons, if you're not too familiar, is basically they're similar to protons and neutrons, but they contain strange quarks, right? So they are confined states of quarks with strangeness in them. They're unstable when we generate them in particle colliders. They quickly decay, but over there they would be stable due to Pauli blocking. Maybe both, we don't know. That's what we're trying to learn, right? Okay, so this is high energy domain. This is middle energy when we have basically weak crusts, and this is low energy, the crust. So let me talk about the low energy things that happen in a neutron star, and that's pretty much the things that happen near the surface. And it's important that we know that, because that's what we can detect. Unfortunately, we have no hope in the near future to detect neutrinos from the neutron star. The neutrinos, they come from the core, but we can't detect them. So what we detect them is the photons, and the photons come from the surface. So we need to know what's happening in the surface. So the things that there happens in the surface, the low energy processes that happen in the surface, are important, and we need to understand them very well. And luckily, we do mostly. So we have this, sorry, it's in Portuguese, the black region is what we call the mantle of a neutron star. So actually, I usually tell my students the name neutron star is pretty much a misnomer. It should be a neutron planet. It's much more like closely related to a planet, because it has a solid crust and a liquid core. But anyways, and that's why we have a mantle in this neutron star. So we have this mantle, which is the crust, and then we have a photosphere. This photosphere, and then it depends on the environment in which the neutron star is found, but usually has a lot of electrons. It has hydrogen. If it's isolated, it's basically just hydrogen. But it could have some fallback in during its formation and all the hydrodynamical processes that happen near the supernova. Some matter could fall back, and then you could have higher, heavier elements in there, up to iron, of course. And that changes a little bit the photosphere properties in the black body spectrum. And through the black body spectrum, we can kind of model this. So we have, and I'm not going to go through details of the models here, but we have thermodynamical model connecting the temperature in the mantle to the temperature of the photosphere, to the luminosity of the photosphere, to the photons of the photosphere, which is what we detect. So we don't even detect the photons that are coming from the mantle. We detect the photons that are coming from the photosphere. And then we have to understand this. So there's a lot of physics going on over here, thermodynamics, and things that are very, very, very nice. Luckily, the photosphere is very thin, so it's basically about 50 meters at most, 20 to 50 meters. And then we don't have we can pretty much, the space is pretty much flat in that region. Not really flat, but it doesn't change, so just a static background. So we can model this. So accretion processes are also very important, because something similar to white dwarfs can happen there. Basically, what you can have is if you're creating process and then you have ions in the crust, those ions can go through fusion process and they will emit X-ray flares. So we have an active state in which you have a strong X-ray flare, and then you have a quiescent state in which the crust is cooling. then you have a flare, and then it cools down. Then you have a flare, and it cools down. And that tells you important thermodynamical information about the core. So this it's all of the hydrodynamics model that people use to study these X-ray bursts coming from the surface. I usually don't do the simulations. I have a very good friend that was a postdoc of mine that have very sophisticated hydrodynamic simulations for the accretion disk itself. But I don't really care much about this. I find it very interesting, but I don't do those simulations. I'm more interested in what happens in the core. I'm sorry, in the crust. And that's the physics that I do mostly. So in the middle range of energy between the core and the crust, some interesting things can happen too. Basically, when we go from the outer core, from the crust, and here it's inverted, right? So the surface of the star would be over here, and the core of the star would be over here. So as I said, in the surface or near the surface, we have ions. They're sitting on a lattice, and as you increase density, these ions become very exotic. So they have very neutron-rich, heavy ions that if you look in the nuclei tables, they're very unstable, but not in the star because they're Pauli blocked. So you can have this huge nuclei with a very, very high neutron rate, very high neutron ratio that usually are unstable, but not over here. And what happens, we shouldn't expect this to go through from this to a liquid, right, in a huge jump. So what we have a transition in which you start to form these weird geometrical shapes. And we call them pasta phases because they can look like cylinders, like a spaghetti or lasagnas or things like that. And of course, those are the geometric shapes that we can model, but there could be even more complicated shapes. But basically, we expect to have this middle region with a very exotic pasta phase. They don't change the global structures of the star, but they're important. They're important for the conduction properties of the matter that we study. So as I said, this is another profile of what we believe of a neutron star. We have this lattice. Then between the lattice and the outer core that forms quantum liquids, that's also most likely under pairing. We have the pasta phase, and then we have the core that we don't really know what's happening there. We're trying to learn. So what are the things, I'm sorry about the Portuguese slides, but what are the things that we can hope and we're trying to understand and learn from this middle energy range? They're still open today. What's the morphology of the magnetic field? We know the magnetic field is relatively high at the surface of a neutron star. Traditional neutron stars have magnetic fields about 10 to the 12, 10 to the 13 Gauss, 10 to the 10, 10 to the 11. Magnetars most likely have magnetic fields 10 to the 14, maybe 10 to the 15 Gauss. What about the inside of the star? How does the magnetic field behave over there? Does it go through all the crust? Is only limited to the surface? It's a dipole that permeates the crust. So those are the things that I'm trying to model, and a lot of people also trying to model. How the magnetic field morphology, what's the morphology of the magnetic field inside of the neutron star? How does it affect the equation of state of the crust, if it does at all? The pasta phases, can they be more complicated than we think? Do we have local or global charge conservation in this region? This is not as relevant today, but it's still something people look into. And the picnonuclear reactions, those are the reactions at low temperatures and high pressure for the ions in the crust. Those are some of the things that we're trying to learn. This, again, going back now to high energy, and this is a diagram that I made, I think, on my PhD. For very different models. Again, the brown and the blue is the low energy stuff that we know fairly well, and the green is the thing that we are pretty confident about: neutrons, protons, electrons, and the red is the question mark, right? Neutrons, protons, hyperons, condensates, deconfined quark matter, we don't know. And of course, the possibility that was invented and it was mentioned here in the chat, about strange quark matter. If we have absolutely strange quark matter, this is not being ruled out. We don't have a smoking gun, but it's a possibility that's investigated, and we still investigate it. And I know I'm about maybe do you let me know, Antonio, how much time I have? I'm almost finished. I'm sorry if I'm taking too long.
Just go ahead.
Okay, it shouldn't be much longer. So one of the things that I usually tell my students that I like very much about the stuff that we do, and this I think works pretty much for all areas of physics, is that we also, even though we specialize in the stuff we do, we should keep our minds open and try to connect things, right? So this is a diagram that I have, and what's written here, for those that don't know Portuguese, is microscopic composition. Then we have the equation of state, and we have the macroscopic structure. And this is true for everything in physics, right? You need to model the microscopic world. Usually we don't measure that directly, right? It's hard to measure that directly. So what we do, we model this, be it by, in our case, by building a model for quarks and protons and neutrons and a Lagrangian and Hamiltonian, whatever it is that you do, we're trying to model the microscopic state. If we're doing, I don't know, electromagnetics and it's trying to study paraelectric or something like that, you also need a relationship between the microscopic electromagnetic world and the things that you measure, the displacement and things like that. So here's the same. We can measure the microscopic world directly. So we build this. And what's the bridge between the microscopic world and the macroscopic world is the equation of state, right? And that's the name of the game. Usually you have an equation of state. And of course, you can do all of it. So some people build this, some people study the microscopic structure. But what's very interesting, at least for me, and that I really like about this, is that we have an equation of state. It's very much quantum. Right, so we have a quantum equation of states. No way, even though it's phenomenological because we don't know QCD and all of that, still an object that's pretty much a quantum object. However, its structure is macroscopic, right? So we have an object that's kilometers large, but it's dominated by quantum mechanics, and that's very interesting. And not only that you also need general relativity. So we have an object that you need to basically pretty much use all of the interactions of physics to model it properly. So we're very fortunate to be able to study this. I feel fortunate anyways. So, and the equation of state is the bridge between these two worlds. And what I like about the cooling, oh, I'm sorry. Yeah, I'll go back there. So this is an example of a few equation of states. Those are old equation of states. They're not very, for today's standards, they're not great. But basically, the pressure as a function of energy density, as I said, we don't have to take temperature into account because the temperature, even though it's high, it's relatively low enough that zero temperature is a very good approach when you calculate the equation of state. Basically, if you put a temperature in there, you're going to have a change of the order of 0.04%. So it's not really worth it. So those are very, very upper limits and lower limits of equation of state. Of course, we have a causality limit, so we cannot have an equation of state that violates causality. And we cannot have an equation of state that's softer. And by softer, I mean the slope is slang in nuclear physics. Softer than the neutron gas, a free neutron gas, non-interacting neutron gas. Of course, there are other observational constraints today based on masses and things that we observe. There's a purely hadronic equation of state. I'm going to show very quickly here what happens if we have a phase transition, right? So basically, if we assume that our neutron star is in this region, okay, what does happen? What does it happen? So basically, you have a phase transition from a hadronic equation of state, and this the reference is not over here, but you can look it up later. So this is a relatively good equation of state that's still being used today, and we've done it in about 12 years, 11 years ago, when I was in Frankfurt. So basically, you have a hadronic equation of state here and a quark equation of state here. And then we can assume two types of phase transitions, which is one with local charge neutrality pretty much a first order phase transition. And then one that's a little bit more realistic with global charge neutrality, in which you can have a mixed phase. So basically you have a smoother transition between those two things. So we have quark matter in this equation of state and hadronic matter here, and a mixed phase in the middle. Then finally, we can study the thermal evolution. Here's in English, good. So thermal evolution is actually very good. I like it very much. It's not going to tell you much about the equation of state, as it's going to tell you a little bit about the composition. And what's good is because it's another way of bridging these two worlds. In order to simulate the thermal evolution, you need to have a very good knowledge of the macroscopic structure and of the microscopic composition. And how does it happen? How does a neutron star cool down? It's basically the opposite of a potato. And I always use this example. Some people that have seen me talk probably have heard this. If you take a potato out of the oven, you leave it in the counter, you want to eat it, you just wait. If you touch it after 10 minutes or 15, I don't know, its surface is going to be cool. If you crack it open, it's going to be hot inside. And neutron star is quite the opposite. It cools from the inside out. Why? Because you have a much stronger neutrino emission in the core. And the neutron star is completely transparent for neutrinos. The free mean path of neutrinos at this densities and temperature is about 100 kilometers. And over here, we have a 10 kilometers object. So this is the difference between, I'm going to skip this because I'm running out of time. So let's go through the equation of state for the thermal evolution. I'm sorry, the equations that govern the thermal evolution. So basically, it's a very traditional, it's a very traditional equation of the heat conduction and heat balance equations in a general relativistic background. So basically, you have to take into account curvature. So we have microscopic properties, basically curvature, mass, radius, and microscopic properties, which is neutrino emissivity, thermal conductivity, and specific heat, which I forgot to highlight over here. And then those are the ingredients that we have. And this is a typical cooling graph. I'm sorry, I'm going a little bit fast because I don't want to hold you here too much longer. So this is a typical, very typical from the same paper that I have used, and I'm not advocating for this model at all. I'm just using it as an example of what you get. So basically, this is the temperature that you would observe here on Earth, basically a redshifted temperature that we can simulate as a function of the age of the star. And here's a few observed data points. So we see that the star cools down much quicker as the mass increases, and that's because we have a stronger neutrino emission. Nowadays, we have a hard time, particularly with this model, and in modeling these guys over here. If we were to see, and I don't know why I didn't put it here, we just finished a paper with a different set of observed data. Now we have basically twice as many more data that we had this time. So we have more observations and better ways of probing this. So usually what we say when the neutron star has this behavior here, they always present this knee. This knee is interesting because this knee signals the point in which the crust, which is solid, and the core, which is liquid, they thermalize, right? Usually happens between 50 and 100 years. And we also have a nice, really, really nice paper in which we explore this that's been just published. So we usually say this is low cooling and this is a fast cooling. Well, we recently learned of some interesting phenomena about this, and we can correlate the thermal relaxation with the mass. So if we are able to measure the thermal relaxation, we might be able to estimate the mass. And this has been recently published in Astrophysical Journal. So as I said, this is the core crust thermal coupling. So we have Cassiopeia, as I mentioned at the beginning. Cassiopeia is a very nice case of a cooling because we were able to, as I said, there's a supernova that happens 300 years ago. It's the strongest radio source in the night sky. It's very weak optically, so you can barely see, but it's hot in terms of X-ray. So Chandra, the satellite, detected X-ray, and it kept measuring for 10 years. And what we have found is that it's cooling down very quickly. Right. It's cooling down very quickly, more quickly than we thought. Today, that's being disputed. It might not be as quick as we thought, but it's still relatively quick. And people have been studying this. And to finish this presentation, I would like to show you something that we're very proud of, which is this dynamical composition that we have taken into account. Let me go through this very quickly. So here it is. So basically, most of the cooling of neutron stars have been done assuming the neutron star is spherically symmetric, which is relatively okay assumption, although not really realistic in the sense that we know all of the neutron stars that we observe, pretty much all of them, either we can see they're rotating or have very strong indication they're rotating. Some actually very quickly, some not so quickly, but still rotating. So if we were to properly, it might be that the rotation doesn't affect much of the cooling, but we wanted to actually calculate this, right? So what we did, we calculate in a completely general relativistic with no approximations other than the approximation of the numerical method itself, but in terms of theory, no approximation on the theory about the structure of a rotating neutron star and the thermal evolution of a rotating neutron star. Of course, this is a very challenging task because then your equations become more complicated. The metric is not the metric that we know. We cannot use we basically have to solve Einstein's equation in the whole space because it's not spherically symmetric. So the outside metric is not Schwarzschild. It's not okay. We can use just Bukowski theorem and say, okay, outside of the neutron stars is spherically symmetric, so we have Schwarzschild. It's not the case, right? So this is not spherical symmetric problem. We have to solve the whole space, and there are techniques for that. We solve it numerically, of course, and then we can calculate the cooling. And I'm going to show the results because I've been through a lot of times. I'm just going to show the animation. So basically what we have here is a neutron star that's rotating with about 300 hertz. This is the rotation axis right over here. And this, I took basically a chunk of the neutron star so we can see what happens inside. Okay, this is the surface temperature distribution, and this is the temperature inside. Initially, this starts as a thermal, so everything is basically as a thermal. And let's see if I can get this. I think I need to take this out. Okay, so let's see the animation of here. So you can see a colder core over here because of the neutron emission. We have a hotter crust that's thinner in the poles because of rotation. They start like a planet. Eventually, the core becomes isothermal, but not the crust. And then eventually, this cold front kind of emerges in the pole and propagates down towards the equator. So this is a very challenging thing, but we're very proud of this. And this is just a tool. And that's why it was well received, because now if we want to simulate something more exotic like accretion or something like that that's happening and that's clearly breaking spherical symmetry, we have a tool that's able to do it. Okay, we can simulate. Just tell us what you want to put in there. Do you want a heat source? Things like that, and then we can do it. And now what we're doing is we're incrementing magnetic field effects. So we're putting magnetic field effects in there to see what happens. So I'm sorry I took a little bit more of time that I was expecting. But just to finish and to motivate mostly students, and you probably have heard this from other people, and this is my final slide. As I show you, this basically is our eyes, right? What we could observe up until 2017. So basically, we had pretty much exhausted the electromagnetic spectrum, right? everything we could measure in the electromagnetic spectrum, we do. All that we can hope to do now is just basically improve our instruments, right? Improve sensitivity, improve trackability, how we can track those things, and which is good, and of course we should do. But what's exciting now is that we've seen the birth of a new spectrum, which is the gravitational wave spectrum. So basically, we are now in a, I usually make this analogy, we are now where Galileo was 500 years ago, right? When he started to look into the sky and see the things, and we have a very narrow optical spectrum. Now we're starting to look into the gravitational spectrum. So far, our instruments are limited. We have a very narrow spectrum of the gravitational wave uh, spectrum, very narrow band, I'm sorry, of the gravitational wave spectrum. But we hope that with a huge and quick technological development that we're having, we're going to expand the spectrum, hopefully. So now we are here in the terrestrial interferometers. Hopefully, with the space-based interferometers and all of the things that people have been talking about, we're going to be able to look in the universe in the whole new spectrum, combining with what we already know, and hopefully this will give us a lot of nice and cool stuff to do. So thank you very much for your attention. I do apologize for me for taking so long. I get excited and I get carried away with this stuff. I hope this was not too simple, not too basic, and then it was able to let you know a little bit more about the stuff that I do.
So, Rodrigo, thank you very much for your very interesting and very nice presentation. It was, for me, it was very pedagogical and very exciting to see what you have been doing. And so I invite everybody to just open the microphone and thank Rodrigo for his very nice presentation. So. Okay, so we had discussions during the presentation, but if somebody wants to ask something, the time is now. So I'm checking the chat. I think the chat, you answered everything, right?
I did, yes. Those things that I have addressed.
Okay. I don't see anybody with raised hand, so
Probably
hopefully people. Sorry?
Probably not for you, but here in Brazil it's lunchtime, so
Yeah.
people. Yeah. Oh, I think Leila has a question.
Leila,
Yeah.
so just
Hey,
go ahead.
thank you. Hi, Rodrigo.
Hi, Leila.
Congratulations for the very nice talk. I really liked it. And I would like to know how the next gravitational wave observations could or could not give us insights concerning the
Neutron star.
quark state of the Newton
Oh yeah, the
star.
quark. Yeah. You see, right up to now, while we observe a neutron star on the gravitational wave, it's right before the merger, right? The spiraling down. I don't know exactly name of the things that we observe. So what we learn a little bit about this is what they call the tidal deformability, that you can calculate and then have this estimates of the tidal deformability of the star. So basically, how much the star can deform. That unfortunately, that is not really enough for us to rule out completely the equation of state, especially because the quark matter is at the very core, so it doesn't change much the tidal deformability unless you have strong quark matter. It does put some limits, if I remember correctly, in the sound speed. So you can model the sound speed, and people have been doing this using the LIGO and NICER and put all of the constraints together, and you have a limit in the sound speed of the matter in the neutron star, and then you can use this to kind of see how much quark you have. So if you put everything together, like the limits and the tidal deformability from the observations in quark stars, in gravitational waves observations, right? With nicer results recently and mass observations and all of that, some people have obtained a limit in which it seems to indicate, but it's still very model dependent, that the quark core should not be too large, right? So it shouldn't occupy much of the star. So basically, what that means is that the transition to quark matter probably happens at the relatively high densities. What density we don't know, but it should be relatively high, as not to have a very large fraction of the neutron star um, composed of quark matter. That seems to be the case, but there's still a lot of ifs in there. What you would actually be very much interesting is if you have, with the time that's coming, and if you have more precise gravitational wave sensitivity in order to measure the post-merger emissions, right? So we now have the ring down, and then there's I don't remember the names. The region after whatever it's left behind. So you could have two neutron stars merging, giving birth not to a black hole, but to a high massive neutron star. What they call a supermassive neutron star that's differentially rotating. And then you have this object that's going to be emitting gravitational waves. That would clarify a lot of information about its interior, because then the whole object, it's basically has a quadrupole moment and it's doing like this and it's emitting gravitational wave. But we cannot measure this right now. That there's been an observation of this object that's people believe that's not a black hole, that it's this merger that gave rise to this very massive neutron star. It's not clear that's a neutron star, but it's what most people think it is. Again, no gravitational waves directly from the objects, but the what's left behind, it's a very high mass of object. But I guess that's it. Yeah.
Yeah, thank you, Rodrigo. And it's good to know that there are prospects in this sense too. Thank you.
Okay, so thank you, Leila and Rodrigo, for the discussion. Further questions, comments? I have a curiosity, actually. So in this last simulation that you have shown about the cooling down of this rotating neutron star, so do you have any particular limitations on the value of this rotation parameter to get some numerical stability? Or
The numerical stability is pretty much nailed down in a way. So the rotation and the deformation, I mean, we have not reached the point in which we have a very highly rotating star that does not converge. The limitation itself is physical, because the neutron star cannot rotate because it's rigidly rotating, right? Which is what we expect for a normal neutron star because of viscosity. So we have a limit in how it can rotate before it sheds mass in its equator. We call it Kepler limit. So depending on the equation of state and on the mass, it cannot be rotating too fast. Otherwise, it would just be ejecting mass from its equator. So it's unstable. So that's the limit. What we're trying to do now, and actually I'm finishing the code, not for the cooling, but because of these recent observations, and the code should be ready in the next few weeks, is for differentially rotating neutron star. And that's a state that probably exists right after the supernova that created a neutron star, and probably after mergers, and have neutron star mergers that can give birth to these supermassive neutron stars. And that might be able to explain a few massive objects. I mean, we don't know, because when it's differentially rotating, you have a higher limit of mass. But it shouldn't be too stable. It should eventually, viscosity starts to take place, and it should, after a while, be rigidly rotated. But it could stay differentially rotating for a while.
But within the physical limit, your code is stable. I mean, you can.
Yes, so far. I mean, we haven't tested everything, but we have tested very extreme cases of equation of state with very high rotation rate, like 700 hertz or even 1,000 hertz, and it's fine. It just takes longer to run.
Qualitatively is the same. The
Yes.
behavior.
Well, yeah, qualitatively is the same basically, but they start becomes a little bit, flattened more, and then you have
Yeah, sure.
different. Yeah.
Very nice. Okay. Okay. So I didn't see any new messages in the chat. I also don't see. I don't see any hand raised. Okay. So with that, I guess we can thank Rodrigo again for his time and patience to
Thank you.
explain this to all of us. So thank you, Rodrigo.
Thank you, guys.
And I will stop recording.
Okay.
Thank you for being around. And
Okay.
stay safe.
Thank you, guys. And again, I apologize for taking a little bit longer.
No, don't worry. It was very nice.
Bye-bye, guys.